Okay, this is Ms. Gorley, and this is the 4-5 lesson on BC Calculus and concavity, points of inflection, and then the second derivative test. So we just did finding increasing and decreasing intervals on a function, and then finding the maximum minimum points, right? So concavity is just the curve of the graph. So if it's concave up, then it's curved up like this picture you have right here. And it's kind of like, if you think about it, it could, I mean, if it was tipped exactly right, it could actually hold fluid or like some water or something in there. Whereas concave down is like this, and obviously no fluid would stay in there, right? It would just fall out. So if you look at it, concave up, look at the slopes here. See how the slope here goes from negative slope. Then when it's at the bottom, it goes to 0, and over here it goes to positive slope. So what is the slope doing as it goes from left to right? Is it getting bigger or smaller? The slope. What do you think? So if the slope starts out negative over here, and then it's 0 where you've got a minimum, and then it's positive when you get over here, is the slope getting bigger or smaller as you move to the right? It's getting bigger, yeah. It's getting bigger. And in fact, you could take any slopes in here, like if I took the slope, say, right here, see how it's a little bit less negative, whereas over here it's more negative. So you got higher negatives over here, and then it goes to 0. Then you get on the other side and you start having a positive slope, and then the slope gets steeper as you go up. So the slope goes from smaller to larger, right? So when it was concave up, the slope of the rate of change of the slope, or the derivative of the derivative, was always getting bigger, or always positive. So that's a second derivative, the rate of change of the slope. So the second derivative determines the concavity. If the second derivative is positive, where it's getting bigger like this all the time, then it's got to be concave up. Whereas the opposite happens on concave down. You can see you started with a positive slope here, went to 0, and then a negative. So it's getting smaller as it goes to the right. So our second derivative being negative, or something getting smaller, is concave down. All right? Why are you smiling so much over there? I'm like, what's going on? Is there something hanging out somewhere? I don't know. Every time you look at me, you smile. It's like, that's not right. I'm just kidding, Susie. Okay. There's no smiling in math. What the heck? Actually, there is, because look at this. This is our little way to remember this. If it's concave up, then when you do the second derivative, you'll get positive. So we think if it's a positive situation, you're smiling, right? Okay, if it's concave down, you'll get a second derivative that's negative. And if you have a negative situation, that's sad. We're frowning, okay? So that's how it helps you remember that. Okay, so this is called a point of inflection on a graph, where it changes from concave up to concave down. So can you see on this graph on the right, where does it change from concave up to concave down? Can you see where it's concave up and concave down? Look at this part over here. Is that part concave up or concave down? Down, yeah. It's not, if you hold that there, it's not going to hold fluid, right? How about the other side? Now, technically that doesn't hold fluid, but kind of like, picture it like if you tilt it sideways a little bit, it would hold some fluid in it, right? That's concave up. So here we have down, and here we have up. So where's the point of inflection? 0, yeah. 0, 0 is the point of inflection. So where they change from concave up to concave down, or vice versa, it's called a point of inflection, and you just give the whole point. It's a point of inflection, so you give the whole point, okay? All right. So same process that we had before, where we're going to do the second derivative. This time, though, instead of it equal to 0, where we find our critical numbers for the concavity. But before we get to that, let's just do it from looking at a picture here. So use the graph at the right to answer these questions. Base your answers on the appearance of the graph. Okay, so on which intervals is the graph concave up? Can you tell? Look, just go straight across them. What about this first section from -2 here? From -2 to -1, it looks like. Can you tell what that is? Yeah, it's barely curved, so it's up, right? Where's another place where it looks like it's up? Yeah, 1 to 3 there. It looks straight to me from 3 to 4. Is yours really straight there too? That looks really straight. Is there any other concave up?
4 to 5.
Yeah, 4 to 5 right there. Okay, so let's write our intervals down then. So we have concave up from -2 to -1. Now concavity, they never include the ends. So it's always parentheses on there. So concave up and up. That's another reason why I like to do parentheses on the increasing and decreasing intervals, because then I don't have to think about, oh, which one is it, you know. I just do parentheses on everything. I think it's easier. Okay, unless I'm doing domain or something like that, then you have to think about including ends and things. All right. Concave down. Where's it concave down? Right, -1 to 1, and where else?
5 to 6.
Yep, 5 to 6. -1 to 1 and 5 to 6.
What about 3 to 5?
3 to 5? Well, from 4 to 5 it was concave up, right? From 3 to 4, what about from 3 to 4? If it's, yeah, what's happening there from 3 to 4? It's straight. So the rate of change never changed. It's always got, it looks like a slope of 1 there. It's got a slope of 1 that entire time, so the second derivative never changed. So that's where it has no concavity, or where the second derivative is, or where the derivative rather is constant. Okay, so this is from 3 to 4. And then you can't see it very well. Can you see it on your graph very well? But the graph actually includes this little line down here too. So right there, from 5 to 6, it's a horizontal line. So that actually also is a place where it's constant from 5 to 6, or 6 to 7, sorry. Did I say 5 to 6? I meant 6 to 7. Okay? So are there any points of inflection? Where's the first one going to be? Yeah, -1. So give the entire point. So it's -1, 1. Right there. Do you see another one? 1, 1. Oh. Sorry, I got to rewind here. Because this is not a point of inflection. Did the derivative exist there? No. So if the derivative doesn't exist there, if it's a sharp point, it's not a point of inflection. Okay, it does change from concave up to concave down, but it has to have a nice derivative there. So our first point of inflection is actually 1, 1, right here. So do you see another point of inflection? It has to change, remember, from concave up to down or down to up, and it has to be nice and smooth. Yeah. 5 what?
1.
Yep, 5, 1. Exactly, those are the 2 points of inflection right there. So this one was not 1. Get over that. All right.
Not just every point, right?
No, and it can't change from going concave up to constant or concave down to constant, like the ones where we said that there was no concavity. It has to change from concave up to concave down, and it has to be a nice smooth change there. Okay? So if you go back up to the actual definition there, it says a point of inflection, the graph has a tangent line at that point, and it changes concavity. So it can't have a tangent line if you have a sharp point on there. Okay, so the derivative has to exist. All right, so analytically, we can find concavity and points of intersection by using the second derivative and doing a number line, just like we did the first derivative, to find increasing and decreasing. So again, you need the domain every time, and you need your critical numbers on your second derivative here. I don't believe they actually call them critical numbers, though, do they? Let me look. They don't. Critical numbers, they call that for the first derivative. But he never actually calls them critical numbers here, so they're just possible points of inflection. How about we call them that? PPIs, possible points of inflection. I think that's what he put in his notes, PPI. Yeah, there it is. Okay, awesome. So determine the points of inflection. So we first have to find all the possible points of inflection by looking at domain and second derivative equal to 0. So what's the domain of any polynomial? All reals. So we have domain is all reals. Okay. Technically, if you're just trying to find points of inflection, does that domain matter that much?
Yeah.
Could you have a point of inflection at a place where the graph doesn't exist?
Because there has to be a point.
Yeah, there has to be a point. So the domain is never going to be, where you have domain restrictions, it's never going to be a point of inflection. But it does help you when you're doing that number line thing. So I always do domain no matter whether I'm doing first derivative or second derivative, I always do it. Okay, so we're just doing concavity. So we just go straight to the second derivative. So do our first derivative here. But we don't have to do anything with that. We can just go directly to the second derivative. Okay, and then it exists everywhere again. So now just set it equal to 0, just like we did in our last section. Let's factor a 6 out. And then factor that. What is that? 2x and x. We want a positive, so I believe that's correct. Okay, once you get your x values, make a number line. This is a second derivative number line here. Remember, that's what we're doing. And we'll put our -1 and the 1/2 on there. And then do the same thing we did before. Check each section into the second derivative in any form. That one, this one, or that one, whatever form you want. Check each section in there. F double prime of something really small, like I'm going to pick something really, really small, like maybe -100. Because I can see right away if I plug in -100 and I square it, that's going to overtake all the other terms. It's going to be positive. Okay. And again, if I plug in something really big, like +100, anything bigger than 1/2, again, I'm going to get a positive there. If I plug something in between, probably 0 is the easiest to plug in between. And I get, what do I get with 0? -6. So there we go. We have our concavity. So we're supposed to discuss the concavity. That means just say where it's concave up and concave down. So concave up from -infinity to -1, and then again from 1/2 to infinity. And concave down from -1 to 1/2. There's our discussion of the concavity. And then it says, determine the points of inflection. So point of inflection happens at -1 and 1. So point of inflection, I'll just call it P of I, is one occurs at -1 and the other one occurs at 1/2. You got to find the y coordinates. How are you going to do that?
Put them back in the table.
Question really quick.
Mhm.
So, how do you know if it's still, if it goes back, I guess, so like the, because, because wouldn't it go up and then be going down in the middle and then back up again, so you have concave up?
Yeah, so if you kind of think about what an x to the 4th graph would look like, what do the x to the 4th graphs look like? Yeah, both ends have to be up, right? So this is saying that both ends are up, but in the middle it went like that. So you've got concave up on this left side and on the right side, and then concave down. Actually, the concavity starts, it's probably like concave up to about there, concave up to there, and then where it changes concavity in the middle, that's that concave down. So this point right there is that -1, and this point right there was at 1/2. At x equals 1/2 on a graph. Okay, so when you plug those back in, what did you get for the entire point? What was -1? -2. What do you get for 1/2? That one's ugly. Yeah, I think it's 7/16. Is that right? Double check, see if that's right.
Yeah.
Okay. All right, so that's how you do it. That's concavity. I love it, like I said, when they're polynomials, just like before. Polynomials, easiest ones to do. Okay, this one's not a polynomial, but look what they did. Isn't this so nice of them? They gave us f of x, and then they gave us the second derivative. We don't even have to do it. How nice is that? So when they're trying to just test, do you understand how to find points of inflection on a more complicated function like this, sometimes they'll give you that. They don't want to know, can you do the derivatives, because you've already shown them that on other parts. So you already have your second derivative here. What's the domain of this function?
X cannot be 2.
Right, x can't be 2, and what else?
-2.
-2 and 2, right? Okay, so those we're going to put them on our little thing here, -2 and 2. Another thing that he does, I always just label them, those are vertical asymptotes. But he actually does, he goes like this and draws like this down them to remind himself that those were vertical asymptotes. You can do whatever you want, just as long as you remember the vertical asymptotes there. Okay. All right, let's take our second derivative then and set that equal to 0. First of all, it doesn't exist at the same places, right? Where x is 2 and -2, so that doesn't matter. But setting our second derivative equal to 0 gives us basically the numerator equal to 0. Where does that equal 0? If you divide by 10, the 10's gone, right? So we're basically saying, where is this equal to 0? Subtract 4, divide by 3. What's the problem here?
It's a square root of a negative.
Square root of a negative. Does it ever equal 0? Yeah, that can never happen. So there's no possible points of inflection here. Okay, it doesn't have any points of inflection on this graph. All right, so we've already got part of our answer. No points of inflection. There's part of our answer. So all we need to do is discuss the concavity. We just need to say whether it's concave up and down. We just need to test in our number line. So you have your second derivative. Plug in a number in each section here, in the left and the middle and the right. I think the easiest in the middle would be 0. And you're going to get a positive over a negative, right, when you plug in a 0. So this middle part is 0. Is negative, sorry. Then plug in something really big to the right or the left. When you plug in, like, think about plugging in 100. It's obviously going to be a positive over a positive, right? Same thing when you plug in -100, because you're squaring them. So there's our number line. So we're going to say it's concave up from -infinity to -2, and then again from 2 to infinity. And it's concave down from -2 to 2. That's all you do every time. You just say where it's concave up, concave down, or where it has no concavity. And then you state the points of inflection. All right, let me see 5 to 0. How are we doing? Everybody, where are we? Awesome, we're all at least at 3. Okay, let's move on. I know she used to not care about anything, and now she's like, oh, cares about her hair and her makeup. It's crazy. Anyway, I never even wore makeup at 12. Did you guys wear makeup at 12? I know. I'm just like, seriously? Whatever. Okay. Okay, so I'm going to have to delete all that out of this lesson. That's at like 19 something. All right, so now we've got we can do our first derivative test. That's our number line for the first derivative. Find increasing and decreasing intervals. Our second derivative test, or not our second derivative test, sorry, the second derivative number line tells you the concavity, putting it on there. But now we're going to do what's called the second derivative test. And everybody wants to think that the second derivative test is that number line we just did, but it's not. The second derivative test doesn't tell you concavity. It tells you about increasing and decreasing intervals. It's weird. So basically, you got to remember this. First derivative test tells you the increasing and decreasing intervals using the number line. Second derivative test is also going to tell you the increasing and decreasing intervals, but it's not going to use a number line. Okay, so those two tests are doing the same thing. They're just using a different method. Then what we just did, where we do the number line on the second derivative, that's not called the second derivative test. That's just the number line with the second derivative tells you concavity. Okay, so get those straight in your head. So this is not going to tell us concavity. It's going to go back to tell us increasing and decreasing again. And technically what it tells us, even more than that, is it tells us specifically at every critical number, is it a relative maximum or a relative minimum? Usually. There's one case when it doesn't give you an answer, but you'll see when we go here. So we're back to first derivative kind of stuff here to start with. So first of all, it says the second derivative test does not always give an answer. If you do the second derivative test and you have a second derivative that's positive or negative, then you can tell what's happening. But if it gives you a second derivative 0, then you have to go back to the old way that we did with the number line, the first derivative test. Okay? So basically, think about it. If you have, say I have a critical number, let's see. Say I have a critical number, like I have a number line maybe, and I have critical numbers at, say, -1 and 1. Okay, so some function. And if it's, let's say it goes plus, minus, plus, like that. So what is this -1? Is that a relative maximum or minimum at x equals -1? Relative max, right? So it's a relative max. And what is it at 1, at x equals 1? Relative what? Minimum, yeah, because it goes down and then up, right? So this graph could have looked something like up to that point and then down to that point, whoops, down to that point, and then up again after that. So maybe something like that, right? Well, look at the concavity. What is the concavity when you had a relative max? It was down. So if I did the second derivative here and I plug in a -1 and I get a negative number, then I know it was concave down at that point. So you don't even have to do a number line. So on this one, if I had just found my critical numbers were x equals plus or minus 1. If I just do the second derivative and I plug in a -1 and I get a negative, I know that this at x equals -1 is a relative maximum because the graph is concave down at that point. So what about over here where it was concave up? That's the relative minimum. What would I have gotten then if I plugged in the second derivative at 1? I would have gotten a positive. So if I do f double prime at 1 and I get a positive, then I know that at x equals 1, I have a relative minimum. Okay? So just think about it, doing your second derivative. So I always think, okay, I get a second derivative that's positive. That means it's kind of shaped like this. Well, that means it had to have a relative minimum right there. Okay? Second derivative that's negative, it's shaped like that. That means I had to have a relative maximum in that area. Okay, so that's the second derivative test, actually. All right, so let's use the second derivative test to find the relative minimum and maximum points on this, all right? Okay, so first thing we need to do is find out the critical numbers first. So first of all, our domain here is all reals, right? Okay, and our critical numbers then, we'll set our derivative equal to 0. So we have negative 12x cubed plus 12x. Set that equal to 0. Factor out a 12 or a negative 12, whichever you want.
You should do 12x.
Yeah, you should take an x out too. Good job. Good catch there. And then that obviously gives us x equals plus or minus 1. And then this one gives us x equals 0. So we have 3 critical numbers. Okay, so you don't even have to make a number line for this. We have the 3 critical numbers. All we're going to do is do the second derivative test, plug them in, and see if we get positive and negative, and we'll know if they're relative maxes or min. Because it didn't say to us to find where it's increasing or decreasing, so if they just want the relative max and min, you can do this test. So our second derivative then is negative 36x squared plus 12. Okay, so we're not trying to find concavity, so we're not going to set this equal to 0 or anything. We're just going to use this with these numbers here now to find out each one of them, are they a relative max or min. So f double prime of 1, negative 1 rather. Plug in a negative 1 there, what do you get? Positive or negative? Negative. So what does that say? Remember, that means the graph looks like that. So what does that say about at x equals negative 1?
It's a maximum.
It's a maximum. So we have a relative max at negative 1, comma, whatever. Does it say the whole? Yeah, they want the whole point, so we're going to have to go back and find that. Well, actually, you could just do it now. Just plug it in up there. Put a 1 up in there back into f of x. What do you get for, or plug a negative 1, sorry, back in. Yeah, you get 3. Okay, now let's do f double prime of 1. Well, isn't that the same thing? It's also negative because you're squaring it right there. Get the same thing on these. So you have another relative max at 1. And again, when you plug that in there, you're going to get another 3. So there's our relative maxes. And then let's try the other one at 0. When you put that in the second derivative, what do you get? Positive. So what's happening there? Relative minimum. So relative minimum is at 0, and then plugging it back in, you get 0. So there you go. So if you don't have to find the increasing and decreasing intervals, and it's easy to find the second derivative, sometimes this is faster to do to find the relative min and max. Technically, though, you never need this, because couldn't you always go and do the number line one? You could, but they do ask questions about it. So you do have to know it. So you can't just abandon it and say, well, it's not really, since I don't really have to use it, I'm not going to. You do need to practice it because they will ask you some specific questions about it. Okay, let's go to part G. Like this is a question where they would ask you specifically about it, where if you don't know the second derivative test, you could be in trouble. So g of x is a function with some derivatives shown in the table there. So you can see you've got your first derivatives and second derivatives shown there. And it says find the x values of the relative maxes and relative minimum points when possible. Okay, so when you had a function that you were doing, how did you find the critical numbers?
Where the first derivative equals 0.
Right, so that's what we got to do here. Where is our first derivative equal to 0? Okay, negative 3, where else?
Everything except 1.
Exactly, all of these. 1 is not a candidate because the derivative isn't 0 there. So even though, so I have a lot of people, they just go directly to looking at the second derivative and they go, oh, it's positive there, that second derivative is positive there, so therefore, because it's positive, that is a relative minimum. But it's not because it wasn't even a critical number. So you first have to check the critical numbers. We've got all of these, and now let's check each one of them. So what x values, let's see, what do they want? They just want to say which ones are relative maximums and which are relative mins. So let's just put them like this. X equals, so let's all write over here. Critical numbers were negative 3, negative 1, 0, and 2, right? So what happens at negative 3? Since I have a positive derivative. Yeah, it's concave up. So what does that make that extrema? Is it a relative max or relative min? Right, that's concave up. It's a relative minimum. So we'll put it under the relative minimum one here. Okay. And what about the next one at negative 1? Or, yeah, at negative 1, the second derivative is negative 1. It's negative, so what's happening there? Right, concave down, so it's a maximum. It'll go over in this column. The next one is 0, and we got 0. What does that tell you? Does the second derivative test help us there? No. It doesn't. So at x equals 0, F double prime, or in this case G double prime, I guess it is. G double prime of x is equal to 0. So second derivative test is inconclusive, which means it doesn't help us a dang thing. On this one, you can't tell what's happening there, so you say it's not possible to tell what's going on. Okay, I can't tell you for sure if that's a max or min. It might be, but I just don't know. Usually what happens there when it's 0, it usually ends up being something like what we got before with our x cubed function, where it wasn't a point of inflection at all, or excuse me, a relative extrema at all. However, it could be. There are cases where it can be. So you just don't know. Okay, what about our last one here then? At x equals 2, what's happening there? Is that a relative max or min? Right, because it's concave up, so it's a relative min at x equals 2. Okay, so relative max at x equals -1, relative min at x equals -3 and 2. Does it say anything about explain on here? Find x. Okay, it doesn't say to explain, but if it had said to explain why on this, then you would say I have a relative max at x equals -1 because G double prime at -1 was, what was it? Was it positive or negative? Negative. Okay. Or technically, that's not really the best way to write that.
Would you say it has a downward concavity?
You can, but you want to say what you use mathematically to come up with that. So you want to say, I was checking this to see if it was less than 0. So that's the best thing you could say right there. You don't want to say is equal to negative. That's just my little notation stuff. But is less than 0 is how we'd want to say that. And then you'd say there's relative minimum at x equals -3 and x equals 2 because, what would I say this time? G double prime of -3 is what? Yeah, greater than 0, and G double prime of 2 is greater than 0. So that would be explaining them on there if they asked you to explain. Okay? And we just don't know at 0 what the heck's going on there. All right, let me see 5 to 0. Can you do these? Everybody? Where are we at? Okay. All right. That's it. That's the whole lesson.